Molecules, Compounds, and Chemical Equations, Part 4. Specifically, what we're going to be looking at today is combustion analysis, which isn't in the AP Chem curriculum anymore, but could be really useful to know for college. Combustion analysis example, because that's really important. Hydrates, and a worked hydrate example, which still is in the AP Chem curriculum. Let's talk about combustion analysis. Compounds that contain carbon and hydrogen only, when burned completely in oxygen, will yield only carbon dioxide and water. Analysis of the mass of carbon dioxide and water produced can be used to determine the empirical formula of the substance in question. This method assumes that all the carbon in the carbon dioxide originated from the carbon in the original compound, and all the hydrogen in the water originated from the hydrogen in the original compound. So let's look at an example of how to walk through combustion analysis. When 4-ketopentanoic acid is analyzed by combustion, a 0.3 gram sample produces 0.579 grams of carbon dioxide and 0.142 grams of water. The acid contains only carbon, hydrogen, and oxygen. What is the empirical formula of the acid? Step 1. Calculate the mass of carbon present in the combusted sample. So I'm going to mention these bullets and then I'm going to walk you through it. Convert the given mass of carbon dioxide to moles of carbon dioxide produced. Since there is one carbon atom in one molecule of carbon dioxide, this is the number of moles of carbon atoms present in the original compound. Convert the moles of carbon atoms to mass of carbon. We look at this and we can say, all right, our total mass sample at the beginning, before combustion, was 0.3 grams. When it's combusted, we produce 0.579 grams of carbon dioxide, and that's what we're going to be working with first. So I'm going to pull this piece of information right here to start with. So 0.579 grams of carbon dioxide. And then we follow the AP Chem mantra, convert to moles. So we're going to go from grams of carbon dioxide to moles of carbon dioxide. So 1 mole of CO2. And I know that the gram formula mass of carbon dioxide is 44 grams of CO2. Okay, so I converted from grams to moles of CO2, and that is our first bullet here. Now, since there is one carbon atom in 1 mole of carbon dioxide, this is the number of moles of carbon atoms present in the original compound. And this little ratio right here is going to be consistent through all of our combustion analysis problems. So there is 1 mole of carbon in 1 mole of carbon dioxide. When we look at the formula for carbon dioxide, there's only 1 carbon here. That's why we have this up here. Finally, convert the moles of carbon atoms to mass of carbon. So I'm in moles of carbon, so now I can say, well, I need to get to mass of carbon. So 1 mole of carbon on the bottom, and carbon has an atomic mass of 12 grams. So now, before I do anything else, I need to go through and make sure that all my units cancel. So grams of carbon dioxide cancels grams of carbon dioxide. Moles of carbon dioxide cancels moles of carbon dioxide, and finally moles of carbon cancels moles of carbon, and I am left with grams of carbon, which is what I want. So I'm going to do all of my calculations here, and my answer should be 0.1579 grams of carbon, and I'm not going to round here. I'm not going to round to significant figures because I will do that at the end. Step 2. Calculate the mass of hydrogen present in the combusted sample. So just like the carbon, we're going to convert the given mass of water to moles of water produced. Since there are 2 hydrogen atoms in 1 molecule of water, multiply this number by 2 to calculate the number of moles of hydrogen atoms present in the original compound. So key here. This is the step that people screw up on. Finally, convert the moles of hydrogen atoms to the mass of hydrogen atoms if necessary. So what does that look like? Well, let's take our given. Here is our mass of water, which is what we need to start with. So 0.142 grams of water. And again, convert to moles. Convert this to moles of water. So the gram formula mass of water is 18 grams per 1 mole of water. Now, this next step is the key one. We need to have moles of hydrogen. And I know that in every 1 mole of H2O, there is 2 moles of hydrogen atoms because of this 2 right here. So important, so important. 2 moles of hydrogen for every 1 mole of water. Finally, we're going to take our moles of hydrogen and convert them into mass of hydrogen, if necessary. Sometimes this isn't necessary, but it's always good to go through the process. 1 mole of hydrogen, 1 gram of hydrogen, and again, I'm going to go through, check my units, grams of water, moles of water, moles of water, moles of hydrogen, and I am left with grams of hydrogen at the end. And again, I'm not going to round. I'm going to take this out a bunch of decimal places. So 0.01577 grams of hydrogen atoms. So at this point, I have my mass of my carbon. I have my mass of my hydrogen. I'm going to go to the next step. If there is another element present, typically oxygen, in the combusted sample, then calculate its mass by subtracting the mass of the carbon and hydrogen from the total mass of the combusted sample. In this problem, we had a total mass of 0.3 grams of a sample. So I'm going to say, all right, our given 0.3000 grams of our original sample. We know from previous data that we calculated, we have 0.1579 grams of carbon. We did that in step 1. Then we're going to subtract out our mass of hydrogen, and that is 0.01577 grams of hydrogen. So from our original sample, subtract out the carbon, subtract out the hydrogen, and what is left over is our mass of oxygen. So 0.12633 grams of oxygen. Definitely not rounding. So now I have 3 key pieces of information. I have my mass of my carbon, my mass of my hydrogen, and my mass of my oxygen. And I can finally take that last step and find the empirical formula. So we're going to take the calculated mass of carbon, hydrogen, and oxygen and convert into moles by dividing by the appropriate mass, just like we've seen before with calculating empirical formulas. Then again, just like we saw before, find the smallest number of moles calculated, divide all the numbers of moles by that number, avoid rounding up or down too much at this stage, and be lenient with significant figures. Okay, so let's start from the top. We have 0.1579 grams of carbon. We have 0.01577 grams of hydrogen. And we just calculated that we have 0.1263 grams of oxygen. Convert to moles. Okay, so I did my setups. 1 mole of carbon, 12 grams of carbon. 1 mole of hydrogen is equal to 1 gram of hydrogen. 1 mole of oxygen, 16 grams of oxygen. And then I worked my problems here. I made sure that my units canceled, grams cancel grams. In all of these situations, I'm going to be left with moles at the end. And then I actually did the calculation. So if you did this for moles of carbon, you should have gotten 0.01315. For hydrogen, 0.01577. And for oxygen, 0.007895. The next step is to look at these 3 numbers and say to yourself, okay, which one is the smallest one? And if you say moles of oxygen, you're correct. So now what I'm going to do is I'm going to divide all of these by moles of oxygen. Okay, so I have these all set up by dividing each one by the moles of oxygen. So the bottom one's the easiest because we know the moles of oxygen divided by itself is going to be 1. For hydrogen, we get 1.9987, and then for carbon, we get 1.66. Now for the hydrogen, that's close enough that if we wanted to round that up to 2, I'd feel pretty comfortable with that. But the 1.66, I don't feel comfortable rounding that up to 2. So I know that I can multiply all of these by 3 and get whole numbers for everything. So 1.66 times 3 is going to give me 5. 1.9987 times 3 is going to give me 6. And 1 times 3 is going to give me 3. So the empirical formula for this particular compound will be C5H6O3, because remember, these numbers that we just calculated are our subscripts in our formula. The results from this previous step should be in a convenient ratio and give the empirical formula. Again, note, it may be that the ratio includes a fraction such as 0.5, 0.250, or 0.33, or 0.66 like we saw in our previous example. If so, then multiply all numbers by 2, 4, or 3 as appropriate to remove the fraction. So important here. Finally, if necessary, use the given molar mass to turn the empirical formula into a molecular formula. But that was not the case in the example that we just did. They did not give us a molecular formula. Therefore, we are fine just leaving it as an empirical formula. Hydrates. Hydrates are formula units with water associated with them. The water molecules are incorporated into the solid structure. So an example, copper 2 sulfate pentahydrate, CuSO4.5H2O. The 5H2O is represented as the pentahydrate over here. Remember now, this dot means plus, not multiply. Strong heating can evaporate the water. When water is removed, the result is an anhydrous without water salt. Let's look at a hydrate example. An 11.73 gram sample of cobalt 2 chloride, something hydrate, is weighed, heated to drive off the water crystallization, cooled, and reweighed until the constant mass 6.410 grams is achieved. Calculate the value of X. So we have two things here. We have the hydrated sample, which is 11.73 grams, and we have the anhydrous sample. And remember, the anhydrous sample is the sample that is at constant mass. This is the sample where all the water has been removed. If I subtract the hydrated sample mass, anhydrous sample mass, which is 6.410 grams, I find the difference of this to be 5.32 grams. This is my mass of water. And this is the first thing that you need to do. So they're going to give you a hydrated sample mass, they're going to give you an anhydrous sample mass, you subtract the two and you find the mass of your water. The next thing to do, of course, is to follow the AP chemistry mantra, which is to convert the mass of water, 5.32 grams of H2O, into moles. So multiplication sign in a line, 1 mole of water over 18 grams of water, because we know that's the gram formula mass of water. So 5.32 times 1 divided by 18 will give me 0.295 moles of water. The next thing that I want to do is take the mass of our anhydrous sample, which is 6.410 grams, and convert that into moles. But you might be saying to yourself, Dr. English, how do I know the formula of my anhydrous sample? Well, they gave it to you. Because remember, up here, they told you that the compound is cobalt 2 chloride. And then it's going to have some type of hydrate associated with it. But the cobalt 2 chloride without the water is your formula of your anhydrous substance. So we're going to put COCl2 down here. 1 mole of COCl2. And I will tell you that the gram formula mass of COCl2 is roughly 129.79 grams. And that's going to equal 0.04938 moles of COCl2. And again, I'm not going to round here too much. Finally, the last step to determine what this X here is to take your moles of water and divide it by the moles of your anhydrous substance, which we know is just your COCl2. So in this case, that's going to be 0.295 divided by 0.04938. And again, in a perfect world, when we divide these two out, we should get a whole number. And if I put this into my calculator, I get 5.97, which I'm pretty comfortable with rounding that up to 6. That means this 6 represents our X. So the full formula here now of our hydrate is COCl2.6H2O. So we have solved for the X in our anhydrous substance. So what is meant by the term constant mass in the equation above? What it means is the mass of the chemical salt with all the water removed. So at constant mass, that is the mass of our anhydrous sample. So what did you learn? We walked through the lengthy process of combustion analysis. We looked at a combustion analysis example. We talked about what is a hydrate, and we worked through a hydrate example. Need more help? Feel free to contact me. Have a great day.